right, people have been wondering, where does gravity come from? They are debating. Gravity could come from the mass. It could be from the curvature of space-time, right? So all different kind of explanations. But according to Newton's explanation, he's the one that came up with this very famous, they call it the universal law of gravitation of Newton's, which is based on to put it simply, it explains that gravity actually comes from mass. Okay, come from mass. Any object that has mass has the ability to attract, right? Now, technically speaking, any object, whether the mass is large or small, it has the ability to attract. So even you stand beside your friend, right? Still, you guys will attract. But how come you guys won't smash into each other, right? It's because of the significance of the gravity, the effect. How large is it? So when talking about gravity, the mass has to be at a huge scale, like the planetary masses, planets, the sun, okay, the galaxies, okay, those huge masses, they have significant effect on the gravity. Okay, so let us look at what does it say. What does the law of gravitation say? So basically, suppose that we have 2 point masses. Now, when this concept was introduced, Newton said that assuming that we have 2 point masses means like all the mass concentrated on one single point instead of like a body. Okay, M1 and M2 separated by a distance r. Oops, let me draw a straight line here. Okay, suppose that we have 2 point masses separated by a distance r. He found that the force of attraction is proportional to the product of the masses. So if you take M1 times M2, the product of the masses is proportional to the force of attraction. M1 is attracting M2 towards it, and M2 also attracting M1 towards it. Okay, they both share the same force, which is proportional to the product of their masses. Now, other than this one, he also found that the force is inversely proportional to the square of the radius, the square of the distance, sorry. Okay, whatever the distance between these 2 points, the square of it is inversely proportional to the gravitational force. Now, from here, this relation, we can actually form a formula. To form a formula, we need to put in a constant, right? We need to put in a constant. So F equals to, if I combine these two, right? So I can write it as F proportional to M1, M2 divided by R squared. Now, if I put an equal sign, then I have to add a constant. For some reason, they chose a G, M1, M2 over R squared. Here we get the formula for gravitational force. So this is the general formula of gravitational force. It's G is the gravitational constant. Okay, what is it? I will explain it later. Okay, and M1, M2 divided by the distance, the mean distance. All right, so we have this one. That means gravity is actually acting on both masses, not only the Earth pulling the objects towards it, but the object also pulling the Earth towards it. And they both experience the same magnitude of force. Okay, now here's a question. How come, if they are both experiencing the same force, right? How come the apple falls towards the Earth and not the Earth fall towards the apple, right? So because they are experiencing the same amount, the same magnitude of forces, how come one move towards another and not the other way around? Now, the reason is this, is because of the relatively huge mass of the Earth, okay, that you can barely see the movement. You can barely see the displacement. The force is the same, but because the Earth has a huge mass, okay, compared to the apple, so the effect, okay, the displacement is negligible. Okay, you cannot see it. All right, so that is why the object falls towards the Earth and the Earth stays almost at rest. Okay, there's no displacement. There's no displacement that can be seen because of the too big difference in the mass. But understand that gravitational force always they act the same between two objects. Okay, that is the first point. Now, then we look at this gravitational constant. What is this? This gravitational constant G. Okay, if I do a little bit of rearrangement, that I see G equals to F times R square over M1, M2. If you put two 1 kg masses at a distance of 1 meter from each other, they found that the force of attraction between this 1 kg substance placed 1 meter apart, they found that the force was about 6.67 times 10 minus 11 Newton. Okay, so meaning that if this one is 1, this one is 1, and R is also 1, then this force is 6.67 times 10 minus 11 Newton. That means our gravitational constant G equals to 6.67 times 10 minus 11. And then our unit, not Newton, is Newton m square. Okay, you can do the derivation, Newton m square over kg, right? So kg minus 2 kg squared. In other words, what is this? This gravitational constant tells us how much force is there when you place two 1 kg objects apart from each other. It turned out that the force is very, very small. Okay, 6.67 times to the negative of 11. Okay, so if you increase the distance and you increase the masses, you can actually calculate it based on the constant here. So that means this gravitational constant is true. They found it to be true everywhere, regardless of the medium, right? The medium between the two bodies. Okay, it can be vacuum, can be air, can be anything. Okay, water, anything. So regardless of the medium, this remains true always. They found that the gravitational constant is always 6.67 times 10 minus 11. Okay, just like pi, you can think of it like pi. What is pi? Pi is actually, where does it come from? It's actually the circumference of the circle, okay, divided by the diameter, right? The ratio of the circumference, 2 pi r divided by the diameter, you get pi, 3.142. Regardless of the size of the circle, you can have a big circle, okay, or a very, very small circle. You divide the circumference by the diameter, you always get 3.142. So it is a universal constant. It can be applied anywhere, everywhere, and any condition. Okay, same with the gravitational constant. Okay, so again, what is the gravitational constant? It tells us about how much forces is acting between 1 kg that is kept 1 meter apart. Now, back in that time, right, when Newton formulated this law, right, he used point masses. Why? Because he wasn't sure about if the force is actually applicable for big bodies. Okay, so back then he wasn't sure. So he just assumed that it is point masses. So if the question asks, okay, what is the assumption that we make here is that we are dealing with point masses, all right? So unlike the Earth, right? The Earth, all the masses is spread out in the diameter, in the circle, in the sphere. But when we're doing the calculation, we are going to assume that all the masses come from the center of the Earth. And also be careful, one thing is that our distance here is between the center to the center. Okay, so meaning that if you're dealing with, like, let's say 2 planets, we take the center of one planet to the center of another planet. Okay, so you need to take into consideration the radius as well, the radius of the planet. Okay, later we'll just look at a few examples, okay? So meaning that if this assumption is based on point masses, but in reality it's not point masses, right? Is you have big bodies, okay, any shape, irregular shaped bodies. That means that this concept is only the basic concept. It's just a basic law, okay? So the Newton's law of gravitation is actually the foundation, the fundamental, the basic law, right? Now, something about the gravitational force, some property about the gravitational force. It is a attraction force only. Okay, so I write it here. Attraction only. There's no repulsion in when we are talking about gravitational force. And also gravitational force regardless of the medium, right? Regardless of the medium. And also it is a long range force. Long range force. It can stretch out to very long distances. The sun is able to attract all 8 planets. Okay, it stretches out very, very long range. So it is a long range force. And it is a field force. What is a field force? Normally we talk about contact force, right? Force required, object required to be in contact for the force to act. But a field force is like a space where if you put an object here, you observe what the object do. It stays at rest. Nothing is applying on it. If the force, you put it here, not touching anything, but it moves like this, suddenly it moves by itself. That means you know that this object is being placed in a field force. What is that field force? It could be gravity, it could be magnetic force. Okay? Now, so force is a vector. Direction, very important. Where is the direction of gravitational force? Between two bodies, the way you label it, not just one arrow, because you have both forces, one attract another, right? So M1 will be attracted towards M2, F, and then M2 will be attracted towards M1, F. Different direction. The direction is different, opposite. And they are acting along the line of the distance, along the line, on the line. Okay, but the magnitude is the same. Direction is different. Okay, now you can actually calculate if the law of gravitation says that any masses has gravity, right? So even a person with a weight, with a mass, still has gravity, technically speaking. Okay, you can actually calculate it. Let's say you stand beside your friend. Okay, what's your mass? Let's say I just take an example, 50 kg. Right, you stand beside your friend, 1 meter. What is the gravitational force attracting both of you? Okay, F equals to, again, G M1, M2 over R squared. Okay, now what is the value of the gravitational constant? Here, right, given here, 6.67 is a fixed value. 6.67 times 10 minus 11, 50 times 60 over 1 square. Okay, you calculate this one, you get very, very small, about approximate to 2 times 10 minus 7 Newton. This force, is it large? No, it's not large. That's why you don't feel it, right? You don't feel it. And this force is -7, almost nano. Okay, so it is negligible. Negligible force. Okay, but it is there. It is there. You can actually calculate it. Any two masses will experience a gravitational pull. Now, for objects on the Earth, of course, all the masses of the object is so small compared to the Earth. So the Earth is the one that dominates everything. Okay, so between any objects on the Earth, all gravitational forces is negligible. So since it's negligible, we don't look at it, right? So we only deal with the planetary motion, motion of the planets, motion of the stars, motion of satellites, is where you see the significance of the law of gravitation. Okay, right, let's go to the next one. So we know that gravity creates acceleration, correct? You have net force, you have acceleration. Now let's say, I'm going to erase this. I'll go to the next slide. Suppose that we have an object on the surface of the earth, okay, in air. The ground, okay, let's say the ground is here at a certain altitude. Now, assuming that all forces acting on the object is the gravitational forces, so F. You already know this one. You can calculate G m1 m2 over r squared. Okay. Now, previously we did what? We did mg, right? We did mg. So now we have a much general equations, gmm over r squared. Okay, so we know that when a force acted by the when a force acted by the earth on the object become a net force, then this object will have an acceleration same direction as the net force F. Okay, so assuming there's no resistance, so it's in free fall, it's under free fall. Right, so applying our Newton's second law, what we know about Newton's second law, F equals to ma, the net force will cause it to accelerate, so F equals to ma. What is this? This is gravity, right? Gravity. And also we know F equals to G m1 m2 over r squared. Okay, which m is which m? Very important. This is the earth. Here's the object, somewhere here. Oops. Over here. Okay, let's say that the object is placed, having a mass m. I'll use lowercase m, and the earth having a case, uppercase m. Okay, and this is the radius of the earth. R. Radius of the earth, how much is the radius? About 6,400 kilometers. Okay, that's the radius of the earth. Okay, now using these two equations, we can equate them, right? This gravity is causing it to accelerate. So F equals to F. I have my ma. What is this m? This m is the mass of the object. So lowercase m equals to G m1. Okay, m1 we take the mass of the earth. We put capital M. Gm. M2 is the mass of the object, right? So mm is between the two objects. Here, our two objects is the earth and the falling object here. So mm over r squared. Okay, you see here. What is this r squared? R squared is the distance between the center of the earth to the center of the object. Remember, we are treating them like point masses. The r is the distance between the point masses. Okay, now the thing is this. For any object close to the surface of the earth, if you compare the altitude from the ground, is it significant if I compare to the radius of the earth, which is 6,400 kilometers? It's actually very small, right? If you drop your object from, let's say, 10 km from the ground, okay, 10 km from the ground, compare your altitude 10 km compared to the radius 6,400 kilometers. 10 km is so small, okay? It's so small that you can barely, you cannot see the effect of it when you do the calculation. So that means for any object close to the surface of the earth, we just assume that it is on the surface of the earth. Meaning that this distance, I just put in the radius of the earth, r. So this equation become ma equals to gm m over r squared. Okay, so because object is very close to the surface, so I would just assume that their distance between the center of the earth and the center of the object is the radius of the earth. Even you are talking about 100 km, still the effect is so small. 100 km compared to 6,400 km, very small. Okay, so when you go to a few thousand, right? You go to a few thousand or a few 10,000, then you'll start to see the effect comes in. So normally when we say how high you can see the effect is when we are talking about the satellite altitude. Okay, satellite altitude, the orbits, the moon, the satellites, any space probe object orbiting around the Earth, right? So for normal object, everything on the Earth, close to the surface, I will just use the radius of the Earth here. Right, so here we get our cube equation, this one. Then I cancel this one cancel, this one cancel. This is the mass of the object, right? So I get A equals to gm over r squared. Okay, what is this? This is acceleration, right? Acceleration, because this acceleration is from the gravity, so I'll call it acceleration due to gravity. That is where your g comes from. When you calculate this, these three are constant. Constant, mass of the Earth is constant, radius of the Earth is constant. When you put in the values, you get, guess what? You get 9.81 ms minus 2. Okay, so acceleration due to gravity, I can just change it to g. This is g at the surface, gs equals to gm over r squared. This is one way you can calculate the acceleration due to gravity using this formula. And another way you can calculate using the equation of motions, right? You learn in kinematics. You can use that to calculate the g. There are many ways to calculate g, but all different methods, you calculate it, you get the same answer, you arrive at the same answer, 9.81 meter per second squared. Okay, now from here, what do we know? Looking at the equations, the g depends on what? The g depends on the distance from the center of the Earth. If the r become bigger, that means if you move higher up, okay, you increase altitude, then what you see, the change in the g changes, the g drops. Okay, so it goes from 9.81, maybe drop to 8 point something, 7 point something, it drops as you increase in altitude. So remember, what we learned so far previously is that the g is a fixed value. That is only true when we are dealing with object at the surface. If you're talking about satellites, they have different g, right? Space station, okay? They have different g. The moon, they are experiencing a much lesser, smaller g because of the altitude here, measured from the Earth. Okay, how does this g affect our life? Okay, you know F equals to mg, right? Mg, so we get our weight from the g actually. Mass and gravitational field strength, right? So if the g decreases, then our weight decreases. Okay, so if the g is half, then our weight becomes half. Right. Okay, now how about, this is for the surface, right? This is for the surface. Let's say, let me change things a little bit. Right. How about we are talking about satellites? That is further up here at a altitude h. Then what would be the g experienced by the satellite? Okay, g surface equals to gm over r squared. Right? What is the general equation? The general equation is this one, g equals to gm over r squared. General equation. This is for g at the surface. Now for g at certain height from the ground, we can write it as gm over r. This one is what? This one, r is measured from the center of Earth to the center of our satellite. So if it's at a certain altitude h above the ground, then we have to add the radius of the Earth with the altitude here. Be careful, here is the, normally here is the common mistakes, okay, that we tend to miss out. The r here is measured r plus h. So r equals to the radius plus the altitude. Not only just the altitude. Sometimes in the question, They give you the altitude when they ask you to calculate the G. So if you only take the altitude, then your answer is wrong. You have to also take the radius of the Earth. Okay, and many students forgot to do that. Remember this one. Okay, so we have R equals to R plus H square. Okay, so R plus H square. This is the G at certain altitude. Okay, now if I want to compare, let's say I want to compare between these two. Let's say I want to find at what altitude where the G experienced by the object is 1/4 of the G at the surface. How do I find that? At what altitude that the G I'm experiencing is only 1/4 of the G I'm experiencing now? At what altitude? Okay, we can solve it, this one here. First, I need to get, because I'm just finding ratio, right? How many the G altitude compared to the G at surface? I want 1/4, right? 1/4. So I need an equation relating these two. So I can just do like this. Equation 1, equation 2, equation 1, equation 2 divided by equation 1. Okay, you see, GH over GS equals to, we have R square over R plus H square, right? Okay, this one I just put it outside. Put it outside, square. Okay, equation 2 divided by equation 1. Then GH equals to R over R plus H square GS. So this is the equation relating them. Just now I said I want 1/4, right? So if I want GH at whatever altitude I'm at, I want it to be 1/4 of G at the surface. What would be the altitude? Then you can solve this. This one is 1/4. So R over R plus H square equals to 1/4. Okay, solving this one, you have R over R plus H equals to square root this. Okay, so 2R equals to R plus H. And then find what is H. You find that H is equals to R. What does it say? If you are at an altitude that is equal to the radius, then your G would be 1/4 of 9.81. Okay, so meaning that here, whatever the radius here, when you're at altitude of R up here, then your G would be only 1/4 of the G that you are experiencing right now. And also, since your G is 1/4, then your weight also decrease, right? Your weight also become 1/4 of your weight right now. Okay, so this is just to show the bottom line. The bottom line is the formula. Okay, first is take note of the formula. This is the general formula. Okay, things to take note. Take note is that G affected by altitude, that's the first one. And also when you do the calculation, the altitude here, remember it is radius plus height. Okay, for satellite, very high up there, take the radius plus the height to find the G there. For any object on the surface, just take the radius, because any object on the surface, we assume it to be on the surface, very close to the surface. Okay, unless your altitude is like the satellite altitude. How much is the satellite altitude? Depends what type of satellite, but normally the typical value would be a few 10,000s. For example, like 3,200 kilometer in kilometer. Okay, so for example, you want to calculate, okay, what is the G of this satellite? G equals to GM over R square, right? Put in the values. The mass of the Earth normally is given, okay, it's given to you 5.97 times 10 power of 24 kilogram. This is the mass of the Earth. G, gravitational constant, also given. So 6.67 times 10 minus 11 times 5.97. Then you divide it by the distance of the center of the satellite to the center of the Earth. So you take 20200 km, you change to m times 3 plus the radius of the Earth, 6400 times 10 power of 3. Okay, then you calculate this, you get the G experienced by the gravity. Okay, you can take note of this slide before I move to the next slide. I will show you a few examples, typical questions that will be asked. And later I'll go to the circular motions, the circular motion and also gravitational law. Okay. Okay, if you are very laggy, try logging in and logging out. Maybe it'll help. Or restart your Wi-Fi, or you try again after 10 minutes. If really cannot, then no choice. You catch the recording tomorrow. Okay, example 1. An asteroid with a mass of 10 to the power of 15 approaches the Earth. Right. If they are this much apart, what is the asteroid resultant acceleration? Resultant acceleration. Okay, first you find the gravitational force. Okay, when it is at this distance. Okay, we do F equals to GMM over R squared, 6.67 times the mass of the asteroid, 10 times 10, 15. Okay, all in SI unit, kg, kg, and R is in meter. Divided by the radius, the mean distance, 200,000,000 square. Okay, so we calculate this. (6.37 times 10, 13 Newton). Okay, so once you get the force, then you can do F equals to MA A equals to F over M. What mass is this? This is the mass of the asteroid. Okay, it is the one that is accelerating. So 6.37 times 10, 13 divided by 15. Okay. What is this? 6.37 times 10 minus 3. Okay, this is my answer. Better or still laggy? Okay, example 2. Two asteroids exert a gravitational force on one another. By what factor would this force change if one asteroid double in mass, the other asteroid triple in mass, and the distance between them quadruple? Okay, this is the one that using the algebra to solve it. So we have the formula F equals to G M. Okay, I'm going to write M1, M2 over R squared. By what factor would this force change, right? So meaning that we need a new force. I'll do it F prime equals to G. M1 is double, 2M1. The other one is triple, 3M2, and the distance is quadruple. Okay, so we have 4R squared. Okay, so this one I continue here. The new F would be 6GM1M2 divided by, this one is square is 16R squared. Okay, like this. Okay, then 3, 8. I get F prime 3 over 8. What is this? This one I can just change this whole thing as my F right here. Okay, put it in. I have F. Here is my answer. It's 3/8. The new force is 3/8 of the original. A bit better, okay. Okay, example 3. Astronaut lands on a planet with the same mass as Earth. Meaning that the planet same mass, but twice the radius. What will be the acceleration due to gravity on this planet in terms of the acceleration due to gravity on the Earth? Okay, then we used our formula G, gravitation acceleration, equals to Gm over for the radius of the Earth, right? R squared. Okay, we can calculate the new G. The new G, G dash, would be same G. The mass here is the same, right? Also, so Gm over the radius here is twice the radius, so 2R squared. Okay, so G prime equals to Gm over 4R squared. We take the 4 out, 1/4 gm over r squared. This one, put it in. We get g prime equals to 1/4 of g. Okay, we continue to the next one. All right, so gravitational law and centripetal force, and how are they related? Suppose that we have an object orbiting around the Earth, so having a linear velocity in these directions. So you have learned about centripetal acceleration and the circular motion, right? So linear velocity, we have two types of quantity. Remember, we have the angular one, we have the linear one. So the linear one is tangential to the circumference. Okay, over here. Let me draw it bigger. Oops. Over here. Okay. Now let's say that we have a object, it could be a satellite, anything, orbiting around the Earth, having a linear velocity towards this direction. Now from point A, when it moved to point B, you have learned that for any circular motion, there must be a centripetal acceleration. There must be a centripetal force. So this centripetal acceleration is the change in velocity. So when it moves here, there will be a change in velocity due to the centripetal force. So the satellite got pulled down to one side here. And now it is moving in this direction over here. Okay, it becomes a new tangent to a new point on the circle over here. Again, from here, point C, it tries to move away to point D. Every time it moves, it tries to escape from the Earth. When it reaches point D, again, you have this centripetal force, pull it downwards, preventing it from leaving. Now it is moving in this direction. So this keeps on repeating like this so that it makes a full circle, because the centripetal acceleration is acting every time, okay, at every point. Now, where does the centripetal force come from? The centripetal force comes from the gravity of the Earth. The satellite is not in contact with anything. It is not on the surface of the Earth. If it was on the surface, for any object on the surface, that will be different because you have reaction, right? You have reaction force. But since it is orbiting in vacuum in space, so there will be no reaction. So all the centripetal force come from the gravitational force. This is very important to understand. If you are talking about object on the surface, then the centripetal force equals to what? Equals to gravitational force minus the reaction, correct? This one you learned in the circular motion, right? So just recall a bit. If you have an object on the surface of the Earth rotating, making a circular motion, then what is your centripetal force? Equals to your mg minus your reaction, because you have a reaction force here, R, and then your mg is towards the middle. Remember, centripetal force is a net force. It is not shown in the diagram. it is not an individual force. It is a net force, not shown in the diagram. Okay, it is the combined effect of the forces. So if mg is bigger, then mg bigger minus smaller, the net force is towards the center. Your centripetal force is towards the center. Okay, but this one, orbiting, it is in space, no reaction. That means the mg, or rather, we would put it gmm over r squared is equals to the centripetal force. Does it make sense? Okay, so here, the natural motion of any object is to go linear in a straight line. What happened to the object here? It is always trying to go out. It is always trying to go out. When it comes here, always it tries to go out, but the Earth also is always trying to pull it. Okay, the V is so large. What V? This linear velocity. The V is so large that it will not fall back into the Earth. So neither will it move towards the Earth, nor will it get away. So there they find a balance between the velocity and the gravitational force. Okay, so here I can write F centripetal force is what? mv squared over r, and gravitational force is gmm over r squared. Okay, since we are dealing with satellite and Earth, so I will take Earth as capital M, this one small m. Okay, capital M is the mass of Earth, and radius also they use capital R. Okay, so from here, I equate them, mv squared over r equals to g mm over r squared. Now, from here, I can derive 3 equations. Okay, let me switch position because I'm not used to this. Okay, let's switch like this. Okay, mv squared over r. Now be careful, we can cross out the m, right? But don't cross the wrong m. This m is the object, right? And this one m is the object. So we have gm over r squared equals to v squared over r. Here. Now from here, very important, the derivation, oftentimes they will ask you to derive. Yes, you need to remember the steps. Okay, so v, first I can get an equation relating v. Okay, meaning that I make the v the subject. So I have v squared equals to gm over r, and bring this r over there, cancel out, and then v equals to square root of gm over r. That is my first one. Here. Normally, you will see these equations. Okay, the one that I boxed is the common ones that you will use. This one is the equation relating the V and the distance of the satellite from the center of the Earth. You can see that the V, this is a constant. This is a constant, this is a constant. So the R, the altitude of the satellite affects how fast it moves, right? The altitude of the satellite affects how fast it moves. If the altitude is high, what happened to the V? If the altitude is high, then the V will be low, right? Would be small. So satellite moves slower at high altitude compared to satellite at lower altitude. Lower altitude, they have to move faster. If you think about logically, it makes sense also because satellite lower altitude, they experience greater pull, right? Because they are nearer to the Earth. So if they experience greater pull, then they have to travel faster. Okay, they have to travel faster. Right. Then second one, from here, I can also derive another equation. What is V? V from your centripetal lesson, V, the linear velocity, is equals to R angular velocity. Correct? V equals to R omega. Now, what is omega? Angular velocity equals to 2 pi frequency. Right? 2 pi frequency. Frequency is 1 over period. That means my angular velocity would be 2 pi over period. Put it inside here. I get V equals to 2 pi r over period, like this. Okay, now put it in the equation here, derive it. Okay, if you do the derivation, you'll get this. All right, the r, I already move it there, so I have gm over r equals to 2 pi r over t squared, like this. Okay, so gm over r equals to, open the square root, so 4 pi square r square over t square. Okay, so I switch this, I put it as gm over 4 pi square equals to r cubed over t square. Okay, you can also do this yourself, huh? Nothing complicated here, just algebra moving, right? So you get this, right? And this is the one that we need. Second one. First one, second one. What is this used for? You see on the left-hand side, what is gm? Is the same value, constant, 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 everything constant. Only variable here is the distance and the period. So this is the distance and period relation, distance and period. The first one is speed, okay, or velocity, and distance. The formula between the orbital speed and also the distance. This is the period and the distance. Okay, now another one from here. Also, I can, okay, from here, gm over r square equals to v square over r. Okay, so I move this one, gm equals to v square, r square over r. Cross, cross, v square r. Okay, v square r. What is v? V is r omega. So if v square, r square omega square, put it in, gm equals r cube omega square. Here we arrive at our third one. What is this formula? This one is relating between distance and also my angular v. Sometimes they call this angular v, sometimes they call it angular frequency or angular speed. Okay, they have many different names. Okay, what is omega? Omega is from the circular motion, angular velocity. Again, gm is a constant. So notice that for any object orbiting a central object, okay, it could be the satellite orbiting the Earth, it could be the Earth orbiting the Sun, it could be the Moon orbiting the Earth, all apply. All of this, example, this formula apply. Okay, so if you take the mean distance, the distance r from the center of the object times into the, let's say this one, angular speed, okay, it actually equals to a constant. Equals to a constant. And you can even use this to calculate what is the speed required for the satellite to move at certain altitude. Okay, let me show you an example. You see, let's say I want to calculate, okay, let me erase this. Let's say I want to send a satellite in outer space, and I want a satellite to go to have a period of 24 hours. That means I want my satellite to move one round in 24 hours. Okay, that is the same as 1 day, right? 1 day. And what is the altitude that I'm going to send it? What is the height? If I want the period to be 24 hours. Okay, given some information we need to know, the mass of the Earth, 5.97, 10 to the power of 24 kg. And the G is 6.67. And then what else? Okay, we need to know the radius of the Earth as well. This one you take 6.4 times 10 to the power of 6 meter. Okay, so given this one, now find what is the height needed. Which formula do we use? We can use this one, right? The middle one. Okay, then we take R GM over 4 pi r squared T squared. All this value I know. G I know, M I know, period I already have. So I can find the R. Okay, so we just do R cubed equals to GMT squared over 4 pi squared equals to 6.67 period. Don't forget to change to second. So period is 24 hours. So times 24 hours times 3,600 to change into second. Don't forget the square over 4 pi square. Okay, can you calculate this? See what you get. Divide by 4 times pi squared. Okay, you get 7. Wait. Oh, cube root. So we have cube root. Cube root your answer. You should get 4.22. 3 significant figure. 4.22 times 10 to the power of 7 meter. Is this the answer? No, because you are calculating what? You are calculating R. R is remember this R is from the center of the Earth to the center of the satellite. So you have to, if you want the altitude, you have to minus the radius of the Earth. So R equals to this one like this. Altitude equals to R minus radius of the Earth. So 4.22 times 10⁷ minus 6.4 times 10 power of 7. You get 3.58 times 10 power of 7. Here's your final answer, meter. Okay, I can just put in km lah. I write it here. 35800 kilometer. Okay, I changed to km. So 35800 kilometer. What is this? This is the height that I need to launch it so that it makes a period of 24 hours around the Earth. Any height higher than this or lower than this, it would not be 24 hours. It's different. Okay, so here the satellite is having a period of 24 hours, same as the rotation of the Earth. What does it mean? It means that here, if you stand here, let's say you stand here, let me erase it. You stand here and the satellite is on top of you. After a quarter of the revolution, since it takes 24 hours to make one whole revolution, right? So you divide by 4, you get 6 hours. 6 hours, it becomes here. Because the Earth is also rotating at the same period. So 6 hours, you also here. After 6 hours, from here you You came to here, and then when you look up, after 6 hours, you look up and you still see the satellite. Right? The satellite is still here. How come it's not moving? Respect to you, it's not moving, right? It's not moving. And then another 6 hours, come down here. You are here, and then you see the satellite again over here. Okay, one revolution to this here. This side, satellite again is always overhead. Okay, always remained on top of you here. So this type of satellite, what do we call it? We call it geostationary. Geostationary. Geo means location. Geolocation is stationary to one location. Okay, it's stationary with respect to one location. We call it geostationary satellite. How high is it from the Earth? You have calculated it, 35800 kilometers from the ground. That is the altitude of geostationary satellite. What is the use of geostationary satellite? Since the period is the same as Earth, right? So that means throughout the day, it focuses on one single point. It doesn't move anywhere. It focuses on one single location. Okay, it is used to communicate with it makes it easy to communicate with the satellite, because all you have to do is just build an antenna. Okay, let's say you want to receive signal from the satellite. Okay, you build an antenna here, and then you just point at the same direction. Okay, you don't have to change the direction of the antenna. You just point at one fixed position, and then it will rotate together. Okay, you don't have to change the direction of the antenna. You can just fix the axis with the satellite, so it always go with it on top of it like this. Okay, so that is the use of geostationary. Application of it: GPS satellite, TV, okay, or internet, or any form of data transmission. Right. So normally a geostationary satellite, where is it located? Is located. We know the altitude, right? But where is it located? Is located at the equator. This is the Earth. Okay, this is us. The equatorial line over here. If you stretch this out, okay, this is the plane of the equator, right? The plane of the equator. So satellite, geostationary satellite would be on the same plane as the equator, same plane, meaning that directly on top of the equator line. Okay, so I would write here, it is located, let me erase this, too crowded here. Oh, we have a message, wait. It's gone back to laggy now. Okay, oh, sad. Maybe is it because of your location problem? Previously, also my internet is very, very bad during this time, like 7 p.m. nighttime is very bad. But I don't know why recently got better already. Okay, so here, the satellite, the location of the satellite, of the geostationary satellite is located exactly radially above the equator. Okay, meaning that the satellite and the Earth, they share the same axis of rotation. Share same axis of rotation. Nine people at home using Wi-Fi, 3 online class, 4 watching drama, and 2 online working. No wonder. That makes sense now. Okay. Okay, another example would be, you want to take this down first? I go to the next. How are we doing on time? What, 8 and 10? Okay. Okay, calculate the mass of the sun using Earth-Sun mean distance of 1.5 times 10, 11 meter. Calculate the mass, right? The three formulas that we have, V equals to Gm over R, and then we have Gm over 4 pi square equals to R3 over T square. And then we have Gm, this was the orbital speed. Okay, the derivation, you have to take note also of the derivation. Okay, so to find the mass with the mean distance, we can use this one also. First and third cannot, because we don't have the velocity and the angular speed, right? So we use the second one. The mass, so mass equals to, I can arrange my formula, mass equals to 4 pi square R cubed over GT square. One thing to take note is that this mass, right, is the mass of the, just now how we derive this, we derive this with the satellite and the Earth, correct? So satellite mass and then the Earth mass is the capital one. This is the Earth mass, the mass of the Earth. So that means that this mass is the mass of central object. Mass of the central object. It's not the mass of the orbiting object. Okay, so if you are talking about the sun and the Earth, here, this is the Earth and the sun over here. The Earth is rotating around it like this. The central object is the sun, right? So Earth is the orbiting object. So in this case, this mass is, whose mass is this? This mass is the mass of the sun. So take note of this. The mass is the mass of the central object. Okay, because when you do the derivation, is the mass of the Earth, right? It is the central object. So if you apply on the Earth rotating around the sun, we can still use the same formula, but the mass, be careful, this is the mass of the sun. Okay, the central object. Right, so we use this one, we can calculate the mass of the sun. This one, constant, mean is already given. And G is constant. How about this one, the period? The period of what? The period of the Earth, the rotating object. The period of the Earth, you know, right? 365. 1 year. When it makes one whole revolution, that's 1 year. Okay, then you can calculate days. This one you want to change to second. 365 times 1 day, 24 hours, 1 hour, 3600 second. change it to second. Okay, so I put it here, mass of the sun equals 4 pi square into this one got cube 6.67 times 24 times 3600. Okay, calculate this. Here goes square. So you'll get 2 times 10 to the power of 30 kg. Okay, answer is 2 times 10 to the power of 30 kilogram. That is the mass of the sun. You can also calculate the mass of the earth using the moon as the orbiting object. Moon, the earth. Again, we assume that circular motion around the earth. So if you apply the same formula, m equals to 4 pi square r cubed over gt square. This mass is, whose mass is this? Our central object, that is the mass of the earth. So if that is the mass of the earth, then my period is the period of the moon. Okay, so use the first one to get the speed. Okay, one more thing. Before I let you do some exercises, is that let's say I want to find what is the satellite speed that is at a height of 20200 kilometer. kilometer. So this is much lower than the geostationary satellite. Okay, geostationary satellite is how high? 358, right? 000. 35800 kilometer. Okay, let's say we have this satellite here orbiting around the Earth at an altitude 20200 km. We want to calculate the linear speed of it, okay, the orbital speed, v. In the context of gravity, they also call this orbital speed. Okay, in the context of gravity, orbital speed, linear speed, right? Same thing. All right, so we calculate this using, we already have the altitude, right? So we can just do v equals to square root of 6.67 into the mass of the central object. Be careful not take the same, not take the wrong mass. That's not the mass of the satellite. It's the mass of the Earth. Divide by the mean distance plus, this one is altitude, right? So 20200 times 10 power of 3, change it to meter. And then you have to plus the radius of the Earth. Radius of the Earth is 6.2 times 10 power of 6. It will be given, okay? It will be given. Approximately 3.87 times 10 power of 3 ms meter per second. So the satellite has to move at this speed in order to orbit at this altitude. I repeat, the satellite has to move at its speed, or you can say this is the minimum speed. The minimum speed for the satellite to move at maintain altitude of 20200 kilometer. What happens if the satellite move below this speed, smaller than this speed? Then what happens? It will start to lose altitude, right? It will start to lose altitude. And what happens is that the satellite will start to spiral inward. It will start to spiral like this, come down, spiral inward, and then eventually fall into the earth, like this. So how do you crash a satellite? For example, like the satellite reaches its lifespan. Okay, how do you crash the satellite? You decrease the speed. Okay, you decrease the speed. So you decrease the speed is like you decrease the altitude. What happens if the speed is larger than this speed? Okay, so if the speed is too large, then the satellite will escape from the gravitational pull. Okay, it will escape from the gravitational pull if the speed is too large, larger than the speed to maintain altitude. So too low, crash, too high, it will escape. So at 3.87 times 10 power 3 is just right for the gravitational force to balance it. Okay, it constantly trying to live and it's constantly pulling it downwards. So it makes a circular motion. All right, so I think we'll wrap it for today. I don't want to go into too much. So the rest I will continue in the coming lessons. Okay, so we'll stop here first. I'll give you your break, 5-minute break, and then I'll send you the exercises. By the way, any question from the last exercise, let me know. If you're having any problem with the exercise, anything that you don't understand, you need further clarification, just reach out. Okay, we'll come back at 27. Okay, we'll come back.